Sorry, this should say cyclobutane. You're going to break your model kits if you try to make cyclopropane. Right. So while if you're still making your model, go ahead and keep making it. Okay, just a quick review. Right. So in this chapter, chapter 4, we're talking about molecular conformation, right, or the energy consequences of a molecule adopting different conformations. Right. So the other day we went over a couple different types of strain that contribute to the overall potential energy of a molecule. Right, and how the changes in conformation are going to either increase that strain energy, right, or relieve some of that strain energy. Right, so when we were talking about torsional strain, we use the molecule ethane, right, and in torsional strain, what interaction is causing the strain, or what interaction would cause the increase in energy? Yeah. Which sigma bond? Good, right? So we have groups of sigma bonds here, right? And they're going to be interacting with the groups of sigma bonds there as we rotate around the central carbon-carbon bond. Right? As we rotate around that bond, these electrons are going to get closer and farther away from these groups of sigma electrons. Okay? Torsional strain does not go beyond that. Right? It's only looking at that specific interaction of the sigma bonds on two bonded atoms. Okay? And so we can say that right? It specifically defines the interaction of sigma electrons separated by only one and not more than one bond. Okay, that's all torsional strains. All right, we also looked at steric strains, so we expanded our ethane molecule up to butane, put two methyl groups on each end, right, or a methyl group on each end. Okay, and we looked at steric strain. Okay, as well as torsional strain. So we said that butane, right, whenever we rotate around that central carbon-carbon bond, C2 to C3, right, we get the same torsional interaction that we would up here. Okay, but there's another element that contributes to the overall potential energy of that system, and that's going to be steric strain. right? So torsional strain is present because there are sigma bonds coming off of these two carbons, right? But we also have to define the interaction of what is beyond those sigma bonds. Okay, so in this case, steric strain is going to be the strain, the energy increase that occurs whenever this group of electrons, right, that group, interacts or tries to exist in the same space as the other group, right? And so this is going to define interaction, or be defined by the interaction of electron groups separated by 3 or more bonds. Right, so we can count the bonds here, 1, 2, 3. Right, what's on the other side of bond 1, what's on the other side of bond 3, those are the things that are interacting. Okay, the mistake that you don't want to make, right, a lot of people look at these and define torsional strain as a hydrogen interacting with another hydrogen. Right, it's not about the atoms. Okay, the things that are interacting are the electrons, right? These negative electrons on the outside of the molecule. Negative electrons interacting with other negative electrons are going to repel, okay, and that's really what causes the strain. Okay, down here, again, it's not these atoms interacting with those atoms, it's the electron cloud around this methyl group interacting or trying to be in the same space as the electron cloud around that methyl group, right? So you have 2 electron clouds trying to get together, and they're going to repel each other because they're electrons. Right? Questions about this? Okay, so the third element of strain that we're going to talk about is something called bond angle strain. Sometimes you'll hear it referred to as ring strain. If it's bond angle strain within a ring system. All right, so let's try to define what bond angle strain is. So up here on the board, I've drawn out the molecule cyclopropane. All right, and who can tell me what the hybridization of each carbon in cyclopropane is going to be? Okay.
sp3.
Awesome. sp3. All right, so if that's an sp3 carbon, what is the bonding geometry around that carbon? Tetrahedral. Right, which means that in a tetrahedral system, those bond angles should be around 109.5 degrees. Okay, and that's based on the fact that whenever we have an sp3 carbon, sp3 center, the orbitals radiating from that center are coming off at exactly 109.5 degrees. Okay. Actual bond angles might be different, right? But the orbitals, the actual atomic orbitals coming out of that center are oriented 109.5 degrees relative to one another. Okay, so, right, so this is an sp3 center, tetrahedral, should be 109.5 degrees. What's the actual carbon-carbon-carbon bond angle in this 3-membered ring?
Would it be 100? Would it be 120? No.
120.
60.
Good, 60 degrees. Okay, so bond angle strain is going to be defined by a deviation from the ideal bond angles. Right? This is an sp3 center. It wants to be 109.5 degrees. Right? But because of the ring, because those 3 carbons are tied up in a ring, it necessarily has to be 60 degrees. Right? The consequences of that are really high bond energy, right? Or another way of saying that, really weak bonds within that 3-membered ring. Right? So if we imagine what the orbitals are doing, it's going to be easy to see why those bonds are weak. So let's So remember, whenever atomic orbitals overlap, hybrid atomic orbitals overlap, right, the most effective orbital overlap is when those orbitals meet end on end, right? Have good orbital overlap, like somebody's shaking your hand, right? So this is effective orbital overlap, and it's going to lead to strong, low energy bonds. Okay, so those hybrid orbitals, when they overlap, they have to approach each other face to face. All right, if we look at cyclopropane, remember, cyclopropane, the carbons are sp3 hybridized, so the orbitals coming off of those carbons are going to be at 109.5 degrees. Right? The orbital angle doesn't change, even though the bonding angle might be different. Does that make sense to everybody? Yeah. Okay, so the orbitals are oriented at 109.5 degrees. What is the consequence of that for orbital overlap? Yeah?
There'll be a really big gap in between like some of the bonds that aren't going to the.
Good. Yeah, I don't want to say that there's a gap, right? But rather than the orbitals meeting head on like this, right? Now they're kind of meeting at an angle, right? So the overlap, the amount that one orbital sees or experiences another orbital is going to be less, right? And so this is poor orbital overlap. Right, which leads to weak sigma bonds, right? Meaning that the system is going to be a high potential energy. Okay, so because those orbitals are not meeting head on, right? Bonds that form are not going to be very strong, they're going to be easy to break, higher potential energy level, right, less stable than regular carbon-carbon bonds. Okay, and you could probably feel that. So if you make cyclobutane, right, if we move to cyclobutane, what are the bond angles within cyclobutane? Yeah.
90.
Good, 90 degrees, right? Square interior bond angles are going to be 90. Again, right, they want to be 109.5 degrees, and so we're deviating from the ideal bond angle. And so the bonds that form between the two carbons, right, maybe I have, these markers are my orbitals, right, rather than the orbitals meeting head on like this to form, get this in front, meeting head on like this to form the bond, right, they're really oriented kind of angularly at one another, right, not pointed directly at one another. Okay, so anytime we deviate from that ideal, we're going to introduce a little bit of bond angle strain, right? The more we deviate, the more bond angle strain there's going to be. Any questions about that? No? All right, so all three of these forces, torsional strain, steric strain, and bond angle strain, they can all be present in a system, right? And the three of those, the balance of the three of those is going to influence the overall low energy conformation of that system, right? So if we look at butane, right, grab your model of butane, okay, we can understand that butane has a good amount of bond angle strain. You probably feel it in your model, right? Your model feels like it wants to break apart. Okay, what about torsional strain? Is there any torsional strain? If that four-membered ring is completely planar, is there any torsional strain? How many people think there's torsional strain? How many people think there's no torsional strain? All right, so if we look down any one carbon-carbon bond within that ring, what do we see? What's the relationship between the sigma bonds on this carbon with the sigma bonds on the carbon in front of it? Yeah.
They align each other.
Good. Do you remember what term we used the other day? Yeah. Eclipsed, right? They're eclipsing one another, right? And when sigma bonds are eclipsing one another, they're as close together as they can be. Okay, so knowing that, who thinks there's torsional strain in this system? Good. Maximum amount, right? When this four-membered ring is planar, there's a maximum amount of torsional strain. Because each of the bonds, no matter which carbon-carbon bond you look down, right, each of those bonds, sigma bonds in the front, are going to be eclipsing the sigma bonds in the back. Yeah.
So would you say for this, then you look at like, not the whole molecule as a whole, but like kind of break it down into pieces?
Yeah, so you break it down into the pieces that are defined by the types of strain, right? So if you're looking for torsional strain, you necessarily have to look down a bond, right, one bond, and assess what's going on with that bond. And when you do that, if you're investigating the whole system, right, you have to look down essentially 4 bonds.
Okay.
Okay. All right, what about steric strain? Is there going to be steric strain in this molecule? How many people think steric strain is present? Right? How many people don't think it's present? Okay. I would say it's not going to be a consideration in this molecule, right? Because the two atoms that would experience steric strain, right, they're bonded together. So we don't have to, worry about this carbon interacting with this carbon, because they're always going to be attached, right? They're always going to be interacting. Right? So the question that I want to answer, right? So this is planar cyclobutane. Can cyclobutane adopt any other conformation? And is that conformation better or worse? So what does your model say? Can you move your model around a little bit? So if you look at my model, right, one thing that I can do is I can slightly bend 2 carbons down, right, and take the other 2 carbons and slightly bend them up. Right? When that happens, right, if I take 2 carbons, kind of fold that molecule in half corner to corner, when that happens, what happens to the torsional strain? How does that affect torsional strain?
Decreases it.
Good. Decreases it, right? So now if you look down any of the carbon-carbon bonds when that 4-membered ring is folded, torsional strain is not minimized, right? But it's certainly not at a maximum, right? Those sigma electron groups are not eclipsing exactly anymore, right? So just by bending a little bit out of plane, that 4-membered ring, cyclobutane, can relieve a good amount of torsional strain. Right? Now, what does that do if we bend cyclobutane? What does that do to the bond angle strain? How does that affect the bond angles? Yeah.
I think it would make them slightly more obtuse. Or it would make them slightly more acute.
Good, good. I appreciate the guess. That's good. Right? So it would make them a little narrower. It would actually increase the bond angle strain a little bit. Right? You could look at it on your model. Try to bend those out of plane. You can see how the bond angles have to come in just a little bit. Okay? In reality, cyclobutane is going to spend most of its time kind of in this bent formation, this bent conformation. Because even though we're increasing bond angle strain, we're relieving some of the torsional strain. Right? So all 3 of these forces, all 3 of these elements of strain are in balance with one another. Right? And we can really see that illustrated in these ring systems, right? So cyclobutane in its lowest energy conformation is going to be kind of bent corner to corner. Right? So if you have a chance to add a carbon, make cyclopentane. And we'll end there today. All right, so And cyclopentane is completely planar. All 5 carbons of that ring are in one plane. How does that affect the torsional strain, or what is the torsional strain going to be in that system?
Would it be even between all of the carbon bonds?
It will be, but is that a high amount of torsional strain, a low amount of torsional strain? So on your model, right, look at your model. Look down any carbon-carbon bond when all 5 of those carbons are in one plane and tell me what you see. Right.
Is the torsional strain going to be max?
Excellent, right? If we look down any carbon-carbon bonds, when all 5 of those carbons are in one plane, you can see that the sigma bonds, right, hydrogen, hydrogen, and this bond to carbon, right, they are all perfectly eclipsed. So in the planar form, right, cyclopentane is going to have a high amount of torsional strain, right? In its planar form, cyclopentane is going to have almost no bond angle strain, right? You could probably feel it in your molecule, how comfortable it is, how easy it was to put together. And that's because the bond angles within the cyclopentane are about 108 degrees, right? So almost close to ideal. So in the planar form, no bond angle strain, or minimal amount of bond angle strain, but a high amount of torsional strain, right? So how can we change the conformation to minimize torsional strain or alleviate some of the torsional strain?
I can push one carbon down and push another carbon up.
Good, right? Just push one of the carbons in the ring down, maybe push another carbon in the ring up, right? So when I do this, just pull one carbon down, right? Now when you look around down any carbon-carbon bond, you can see that the torsional strain is going to be much less, right? There's not an eclipsing interaction. There's only one eclipsing interaction really, and that's between these 2 carbons on the back end, right? And so the analogy that people use to describe this, they say it looks like an envelope, right? And so this would be the flap that folds over the top of the envelope, right? So in its lowest energy form, cyclopentane is going to have 1 carbon bent down, right? And that's because the torsional strain is alleviated. When we do this, right, realize that we're introducing just a little bit more of the bond angle strain, right? So again, it's a trade-off. We alleviate the torsional strain, right, reduce that tension, but we introduce a little bit of bond angle or ring strain into the system. Okay, so we're constantly balancing those things. All right, we'll end there. On Friday, we're going to look at cyclohexane. So please come to class with a cyclohexane molecule made. When you make that cyclohexane, attach the hydrogen. It's going to do nothing if you just have 6 carbons in a ring, right? The hydrogens have to be there. So, kind of. I mean, if you look at what's going on, right? If you bring this down, and then you bring this one down, it's essentially like bringing this one up and all 4 of those things. Yep, and again, you have these 4 on one plane. Yeah. I mean, you're right. And this molecule, right, it's not just going to be